not regular.
Okay, so I need to finish the last two pieces, the last two rules of limits that I didn't quite get to yesterday. Let me tuck those in here. One of the nice things about limit behavior is that we can look not just at a single function, but we can look at functions jointly. So there's a result called the comparison theorem. So let's suppose I have two functions f and g. And in a region near some point A, I know that f is always less than or equal to g. Then, if I take the limit, specifically at that point A, for each of those functions, this inequality stays the same. If f is always smaller than g, near A, well, then that means that if I'm coming from the left, f is smaller than g. If I'm coming from the right, f is smaller than g. As I keep coming in, that inequality is going to stay preserved. Now, this in a region near A is a little fuzzy at the moment. But if I want to be pedantic and technical about it, I'd really say that a region near a point is some little interval. A little bit to the left of A, a little bit to the right of A. So this region near A is really a minus some value, a plus some value. And it doesn't even have to be the same value on each side. It just has to be sufficient. Some value, literally, the word, some value. But in my head, I really just see a picture. I see my two functions, f and g. And near A, so cut off some piece of the graph and only look inside that section. Okay, chop. As you get closer and closer to A, f is always on top of g. So the limit, as we get right to the value A, should preserve that inequality. The more technically mathy we get, we can talk about the preservation of order in limits. More on that way down the line. Questions? Okay, so what? Who cares? I want to compute this limit. I have a problem. As we get closer and closer to 0, what happens to sine of 1 over x? We've seen that one before. Sure about that? As x gets smaller, 1 over x gets bigger, right? What's the graph of sine look like? Wiggling back and forth, but we're we're getting bigger and bigger and bigger and bigger. It's going to go back and forth and back and forth and back and forth, right? But I've squished that in right around 0. So we're going to go back and forth and back and forth and back and forth a whole bunch. This doesn't settle down. It doesn't have a limit. That x squared does have a limit. So in one sense, I can think of the sine term as bouncing around like it's psychotic, and that x squared is going, I know what x squared does. That's a parabola. That's nice and easy. So I have easy term and effed up term, and I don't know how to make them talk nice to each other. So let's do a comparison. Something I happen to know about the graph of sine. When we talk about sine, we know it's going back and forth, up and down, up and down, up and down. What's the biggest value you ever get out of sine? 1. What's the smallest value you ever get out of sine? So I know all the time. I know sine of whatever is between -1 and 1. For all x near 0. Notice that word near again here. That's some small region around 0. Let's take this entire expression. Multiply each of those pieces by x squared. You with me so far? If I think about the graph of sine of 1 over x, it's never bigger than 1. It's never smaller than -1. So if I multiply by x squared is always positive. I've preserved that inequality. I've kept those inequalities in the same order. I can compare functions using my comparison theorem right there. By the comparison theorem, I know that's true. I don't know the limit in the middle. Sorry, this left-hand limit. Limit as x goes to 0 by x squared sine 1 over x. I don't know what that is. But what's this thing on the right? What's the value of this limit? I'm hearing mumbling. That's just 0. But I only use these two functions. Let's use these two. Again, with the same idea, what does my comparison theorem tell me? If the function on the left is smaller than or equal to the function on the right near 0, then the limits will have the same inequality. This time, the limit on the right is the one I don't know. I don't know that, but I do know this. What's that limit? Hey, wait a second. If I glue the inequalities together, I can glue these inequalities together. The thing on the top of the screen right now says that the limit of x squared sine 1 over x is less than or equal to 0. This limit right here says that the limit of x squared sine 1 over x is bigger than or equal to 0. What's the only number that's trapped between 0 and 0? I never figured the limit out directly, but I was able to squeeze it between two other functions. And the fact that those two other functions had exactly the same limit forced my unknown graph to go between them and get squeezed to exactly the same place. So let me write this out in detail. The squeeze theorem. If f of x is less than or equal to g of x is less than or equal to h of x in some region near A, and limit as x approaches A of f of x equals L, and limit as x approaches A h of x equals L. F and H are the outside ones. G is the one trapped in the middle. Then the limit as x approaches A of G of x must also be L. If the outside pieces squeeze together at this spot, then the one trapped in the middle must also get stuck there. Page 101, bottom of the page, is the squeeze theorem in a box on the page. But the piece that matters to me, again, is the picture next to it. F of x in blue is the bottom function, g of x in red is the middle, and h of x in green is the top. And notice that at A, f and h touch. And g's trapped in the middle, it must get brought along for the ride. On the top of page 102, our exact example appears in a graph showing you the trap. That psychotic wiggling back and forth always stays between the up parabola and the down parabola. The down parabola and the up parabola touch at 0. So limits obey inequalities in a nice fashion. Whew. The squeeze theorem is a powerful tool because it allows me to calculate a limit indirectly. So we're going to use it in cases where we don't know how to get a limit in another way. Try and find nice things to compare to. Questions? Well, with that being said, those were the last two things I wanted to cover in Chapter 2, Section 3, and that means the ball is now completely in your court. A typical question and answer day. I will answer any question you have regarding Chapters 2, Sections 1, 2, and 3. What do you want to ask me? Nicolina, talk to me.
How do we figure out who the number is instantaneous based?
The instantaneous rate of change is going to be the slope of my tangent line on my graph. You look at me like I've lost my mind. Which problem are you thinking about?
It's 2.1 question 6.
Okay.
And it just says using the graph is it like instantaneous?
Wait, 6b?
Yeah. Or
it just says estimate instantaneous, right? So the instantaneous velocity should be what I would think of as the slope of the tangent line on my graph. But that means these numbers that we got here are all secant lines. So if I say, hey, notice that these second numbers are getting closer and closer to 1, the results from those slopes, those average velocities, should be approaching some number. I don't know what that number is right off the top of my head, but that number that they are all getting closer and closer to should be my instantaneous velocity. I'm measuring what happened between 1 second and 2 seconds. Now I'm measuring what happened between 1 and 1.5, between 1 and 1.1, between 1 and 1.01, between 1 and 1.001. It's basically like I'm not letting it move, right? All right, so those velocities, instead of averaging, now become an instant. Like our secant points became a tangent point. So really, I'm looking for a limit. But at this point in time, we didn't actually have the verbiage to say, hey, take a limit. Better? Angela? They are going to look very similar. So I'm going to make up a picture and just hope for the best. So in problem 2.1, number 4, I don't know what the curve looks like, so I'm going to guess. Here's my point P. And we're looking at secant lines, means I'm going to have another point way over here. And I'm going to draw the line that connects those two. That's a secant. But it's got to go through both points, right? Need my ruler, which is interesting. And if I pick another point that's on the other side, I'd get a different secant line, right? But with my calculations in part A, I was able to say, I know what the slope of the secant line is because I computed it in part A. In part B, we gave a guess as to what we think the slope of the tangent line is, right? The tangent line should not touch either of these other points, but should really only go through the point P itself. Tangent means just touching. So we're only touching that one point on our graph. Now, in this case, the way I've drawn this picture, you'll notice that my tangent line actually seems to cut through the graph. That's okay. That might happen depending on what actual function we have. And yes, I actually think in this particular problem, your secant lines and your tangent lines look really, really close. So you might want to then pick some further away secant points rather than really close secant points. That's the best part about it. It didn't tell you which secant lines to draw. I think there's another one. We actually have to draw 5 lines. All 4 of the secant lines you computed and the tangent line. That might be from the old edition of the book. I'm not sure I remember. More questions? Yes, Nicolai. Well, I mean, I'd like to get a better graph than this, so I don't know, what's the equation in question?
Y. 0.5.
There's got to be an x somewhere in there. It's cosine pi x, right? The original equation looks like that. Whoop, like that. The point we're looking at is 0.5, right? The x value of our point P is 0.5. Wait a minute. Trig question. That pi inside the cosine function, what does it do to the graph? Trig functions are periodic. This changes the period somehow. Anybody remember how? I send you back to trig class. I'm multiplying on the inside. If I was multiplying on the outside, it would change the amplitude. Multiplying on the inside changed the period. How? Did it shorten it or did it lengthen it? Stuff on the inside works the opposite stuff on the outside does. If I multiply on the outside by a big number, it gets bigger. If I multiply on the inside by a big number, it gets smaller. Long time ago, I learned a formula. What's the normal period of one sine curve? When it goes up and down and comes back up, what's the period? Mumble, mumble, mumble. 2 pi. 2 pi to go all the way around. We gotta go around the unit circle once. That's an angle of 2 pi. I take 2 pi and divide by that number. The period of this function is 2. Which means in order for me to see everything that's going on, I only need to look between 0 and 2. Since I'm looking at 0.5, I really only need to look between 0 and 1. Why do I know I only need to go as high as -1 and as low as, as low as -1 and as high as 1? Trig function only goes to -1 and 1. There's my cosine graph. Nicolino, what was our point P?
0.5.
That's an x value. Give me the other part. That's the point I'm looking at, right? I'm trying to get a line tangent right there. So in part B, you guessed the tangent line slope, right? In part B, you came up with a value for this. What you think the tangent line slope should be. So I don't know what that slope is right now, but you got a guess from part B that says the slope of the tangent line is. Give me that number. What did you come up with? Oh, give me a number, whatever number you got. Yes, I'm pretty sure you did it wrong, but that's okay. We'll keep talking about it. Double check your calculator. Ladies and gentlemen, this is where I start to jump up and down and get ugly about it. Double check your calculator. If you are not in radians, I guarantee you this problem is wrong. If you're in radians, you'll get this closer. So, somebody else give me a number. What did you think the slope was? 3.15? Positive or negative? See, I hear a bunch of people. So let me just think about this for a second. I'm looking at the slope of a tangent line. Is the line that goes through this spot going to be going up or down? So I think my slope should be negative, since as I go from left to right, I'm going down. Let me run with the negative version of the number you just gave me. Wait a minute. I know the point we're going through is 0.5 comma 0, right? You have a slope, you have a point. Give me the equation for a line. No, give me the equation for this line. That's my point slope equation for a line, right? Y minus y0 equals mx minus x0. I'm just going to write this y equals minus 3.15 x minus 0.5. Ready for the best part? I can put that line in right here as y2. I can graph the line directly on here. No, it should be, and I didn't write it in. Good catch. So let me go back to the beginning and hit insert and then a minus sign. Please notice I did it on purpose here. There are two different negatives in this picture, aren't there? The minus sign here is only 3 pixels wide. The minus sign here is 5 pixels wide. Look at the keyboard. This one represents subtraction. This one represents a negative. Please make sure you use the right minus sign in the right place, or you will F something up. Well, now I've got this, if I'm right, I've got the graph and the tangent line. Does that look like a tangent line to you? Looks like it's really touching, it's very close all the way through here. We could zoom in. If you've got the color version of this calculator, you can make them different colors. If you want to do this on Desmos, fine. You want to do this on the grapher that's built into the MacBook, that's fine. You can change colors on any of these. If you've never used the MacBook grapher, you go to your applications launcher. It's under utilities, other, grapher. It'll graph for you right here on the MacBook. I use it all the time, so I put mine on my taskbar. Boink. So here's what my grapher looks like. This is a two-dimensional graph. Up there it says y equals. I can type in the equation, cosine of pi. You can get a pi two different ways. See this little sigma symbol in the upper right corner? The little down arrow next to it? If you click on that, a bunch of symbols come up. But the computer knows what pi is. You can type the word pi, and it turns it into the pi. Y equals cosine pi x. There's your graph. You can type the line in the same way. You can then actually print this picture. Hand sketching is not required. You also get secant lines, right? In part A, you got a bunch of secant lines. You have slopes, you have points. You can put the secant lines on here. Doing this by hand is not a requirement. We have the technology. We can rebuild it. You can make this, and then you can readjust the frame. You want to make this zoomed in so that we see the right spots better. We zoom in. Grab it, and you can move it over so you can see the part you want. Cut it, paste it into a document, print it. Your call. If you printed it, you printed it. Print it out on the printer out here and then attach to your homework. Make sure you put the problem number and your name on it so I know whose is whose.
But we can't do a graph by hand.
If you drew it by hand, that's perfectly fine. I am not out to judge your artwork. I'd like it to be close to the right thing, but I am not an artiste. I majored in math for a reason. Once I've got a graph, by the way, if I click on this equation, there's this inspector thing in the upper right corner. And if I click on that, if I click on it properly, it opens up this other little thing, which allows me to change the color. Or the line itself, I could make it a dashed line or a small dash line or a big alternating. So you can, if you have multiple graphs on the same thing, you can use that to tell them apart. If you don't want to print in color, that's fine. Just make the lines different styles and you can tell them apart from one another. Better? Nicolina? Maya? Better? Okay. The question is getting here. Figuring out the top part. Okay. What was one of the X values we used? .49. I'm just going to use 0.49. If I hit trace, and type in 0.49, it gives me a y value. That minus 0, because that's the y value for this point, and then 0.49 minus 0.5. Okay. Oh, no problem. If this is not the number you're getting, the most easiest responses, you might be in degrees. You might have mistyped the equation, both of which are possible. Back in the archaic days before I had a calculator that did this sort of crap, I did this with a giant trig table. I don't want you to do that. And that's why we have technology now. So we'll look at that later. More people ask me more questions. Yes, ma'am.
Questions. 38.
Okay.
Is it okay if I did a chart?
Sure. It just asks you to tell me what this limit is. It says it's an infinite limit, so it's either positive infinity or negative infinity. And you can do a chart, you can draw a graph, you can do all sorts of options to tell me what that is. Somewhere down the line, we'll develop better techniques that are algebraic in nature, but we don't have them yet. Yep.
26.
Same section?
Yes.
26.
Are we supposed to plug in the 5 by 2 max and then 5 by 2?
Yep. That's our equation, just like this. Nope, because we're not in that section yet. 5 to the x minus 1 divided by x. There we go. Hey, that looks like it's got a limit at 0. But there's our picture. I know you took calculus already, but the classes have started. We can't even get.
Like this though, like we did not do this much trig, especially this early on. So trig is thrown off it. So other than that, it's good.
Early. Yeah, I brought it in early on purpose because I'm of the opinion that actually the most useful pieces are stuff that are related to trig functions, not polynomials. Polynomials are quote too simple to work with most of the time. The trig stuff is where the interesting stuff happens. E is where interesting things happen. Logarithms are really freaking cool. It's a crazy name for a power. That's all it is. Logarithms are just powers. That's the definition for a logarithm. It's the appropriate power that I use on a base of 2 to get y. So a logarithm is just a fancy word for a power.
Like I just wanted like
The whole
the history of math. I wanted the history of logarithms.
Ready for the history lesson? Okay. In 1500, 1600, the biggest piece of mathematical use was astronomy. At the end of the Islamic, for lack of a better term, not quite Ottoman Empire, the wars, the holy wars and the crusades were all about the two different religions fighting back and forth. A bunch of people who are Islamic, all the Muslims needed to know two things. They need to know what direction is east so I can pray to Mecca and what time of day is it. So they needed really accurate clocks and really good observations of the sun and the stars. So they built astronomy observatories everywhere. They gathered all this data and people started keeping track of these things, and they realized they were going to use Pythagoras to figure out the triangle between these two stars, and the numbers were effing huge. A guy by the name of John Napier says, if I look at them like powers, when you multiply things, what do you do with powers? Well, but if you multiply things, you take the powers and you add them. So I can turn multiplying into adding if I just think about powers. So let me convert these calculations to powers, and then I can do all of this. And he worked out a table of logarithms, a table of powers, and he took his multiplication idea and turned it into the powers. He actually built a calculator that if you gave it a number and told it what the base was, it would compute the logarithm. There were a series of sticks with numbers written on them in little triangular paths. Unfortunately, Napier was a deadbeat and got thrown into, in Britain, if you owed people enough money, they'd throw you in jail. They called it debtor's prison. Napier went to debtor's prison, but instead of sitting there like a lump, he kept working on this stuff. And it's rumored that he made the first actual physical logarithm calculator out of his former cellmate. They were nicknamed Napier's Bones. There is a set in the British Royal Museum that are actually carved ivory. It's just a fancy name for a power. Okay, I wandered well off topic. Bring me back to calculus, people. What's next?
We're approaching limits, it says like age of 2 and has like an open dot, is it just
So let's take a look at 5 right above it. Okay. If I'm looking as we approach 3 from the left, there's an open circle there, right? But what's that y value? So my limit as I approach from the left is 1. As I approach from the right, what's that y value? So there's the limit, but the actual dot is here. What's the value of h of 3? It's 3. So notice that the limit from the left, the limit from the right, and the value of the function there can all have different values. When I do the same thing with the picture you're looking at for number 6, I'm going to treat it the same way. What am I doing as I get close to, regardless of whether there's a circle there or a dot there? Well, where's the dot? There you go. If there's no dot, then it's undefined. If there is a dot somewhere, then it's defined. Even if that dot has, like look at 2. Is there any dot that goes with x equals 2? I don't see one. No matter how far up or down I go from 2, there's no dot there. So there's no value. But there is clearly a limit. In spite of the fact that there's a hole, there is clearly a limit as we approach 2. Yes, ma'am. Mm-hmm. Yeah. Once you've got this function, yeah, you can just plug closer and closer to 0. You just know that they're going to 0. So get close to 0. Some negative, some positive, go to town. See, in this, if I'm looking at the limit, I'm looking at the graph. If I'm looking at the limit, I'm looking at the graph. I'm not looking at the dot unless I'm looking at the value. Right, because there's no place for me to put the dot. Where do I land? I don't. Somebody asked me another question. I'll come wandering around and ask you a question. Yes, sir. I believe it is 2.5 weeks from today. The 22nd. Yes, ma'am. Ah, 2.1 through 3.1. that dash, sorry. Through all of chapter 2 and section 3, point 1. Oh, yeah. It's everything. Right, I'm using X's that are bigger than my value. No. A lot of people do.
Yeah.
I've got a half an hour of time with your names left on it. I get paid whether you ask me anything or not. Talk to me, people. It's your money. You spent it on a half an hour of my time. Please, let's get your money's worth. Yes, ma'am. I can absolutely come with. I'll keep working. We'll come around the whole room out there.
I did. I just am so excited. I don't, because I just had extra.
Yes.
No, I didn't.
Right, if I do that. And I do it some time. That's this number.
Oh, because but I didn't plug in the X.
I would put that in the program. Why not do this?
So we're finding that's so I have these numbers for I just didn't put them in here. What is this one? What I so these just need flips. Is not. Yeah. Which. So I'm just gonna get the. I think it did speak to. And you're. Yeah. Yes. I think it's very well. It's all messed up. So that is the cut. So you see, I just want to say. So like I'm negative to you. I like this. I understand. Yes. Thanks for this year. I can be so certainly so. This photo. So then yes, also. Yeah, so. Yeah. I want to do it. I saw one. Yeah. Six. Like, look at that. You probably should. Yeah, you think that there's. I'm good. It was, I was so much like. Now I go. I have to make this up fresh. Get over that. Yeah. So. Forty-nine times three is 147. But plus one, and then so it's 143.
What?
Yeah. Wait, five, six. Wait, so what do you get for the fraction? 37.
Right.
I understand. Yeah. So the other ones are all. This world. I will give that. But then she asked me about these three number 25 staff for yes, you know, separated. So I don't.
This is kind of, but I think, so like a lot of others. I figured it out.
So just back and forth now, okay, he's gonna write this and takes this.
I can write X. I can write X minus.
I always need X. Yeah, X plus, yeah. You got plus yes. And then also, except the other side.
Right.
And what else? Oh, yeah, you did excellent. You did so then it goes looking back.
So, are you sure it says like as, and then I'm going to change the page, something like that. So. This one will be approaching, that's big. So this, that's why, yeah, this one is already like, here, that's like, okay. So that one is. And then, right. So everyone. I always extend this around, extending the race. Yeah. And that way, that's started to execute it. But this one.
Also factored out 20. Oh, yeah. Oh, I did like this. What I did was at first, I distributed the squares, right? Because this is also and the thing is, if I have to body stuff, this is or this is all the way to the start of this.
I promise I'm setting these problems up. So if you think this isn't math enough, that's on purpose. We don't have the math is not perfect yet.
Just that.
That's what really gets me. But does that mean the question?
It's over zero, but that.
You nailed it. Keep talking to me, people.
So I have my books again. But I haven't had it, so I want to play that first. So I see the job. I get that. Yeah, this is the life. So I can see all over here. I'm not so challenged. Then I probably should start to run the back. Oh, it depends. Yeah. That's not. Yeah, that's what I got. Okay. Thank you. You did. Where? Okay, perfect.
The problem is you use the old. Which is okay, because I used the old one last year, right?
Does not exist. This one, we'll start with making certain. Then be able to see what this one is completely inside, but I think that's not. Yeah. Also, you do have to score, right? That's just not popular. Yes. So like if I'm pulling, if I'm taking the books, so the H squared minus. Your name comes from the space bar. No. You know where it is. Okay. I know. Also, the list is there's too much. Yeah, that's just how it's. It's always.
Well, this says.
Okay, so that's. So it's basically, it's the extra where. What about the negative 6, 8? That's plus 9, and then yes. Yeah, and then it's just okay. So that turns into. What is the problem? Where and. H minus us. So that equals 66. I'm gonna guess it. So you. So it's like. That's like my. Now my friend. But, so yeah, that's.
Yeah. Because that's what I want to talk about. Oh, wait, no, you're so love writing these cases, I did so. Thank you. So. Okay, so like, I was, I brought it up with the game, here's me, so I'm then you can put some question on it.
Think about it. That's it. A function that only works for the left. A function only works for the right.
Yeah, I actually think.
Them all.
Right, so. Oh.
As long as those two things. You can. But right now, it's like- Yeah, I've only got the part of that. Why would I chop it? You're not gonna chop it off. Oh. Really want to chop that house. You make one, okay. Then draw this one. And chop it off. I'm gonna chop that off. Come around. Draw those two halves. Well, close.
This is what I said.
Just where it closes.
Then the closer it is, just saying. No. I'm gonna try later. I tried to write this.
I want her on paper tomorrow. This is your reminder.
Around 6. Yeah. That's my mental brain is around. 6:44.
But keep in mind this. So. Thing is, you can have it on one side, you don't have it in the one that's very long. And then, so I take a note that I only base it on the left side. Good, I know.
No, it's an accident. I forget.
Well, I'm sure I just.
So you did one and one. So my parents just walked.
I think I read one of the most. Yeah. 20 years ago, I had it. So it probably should be around. Yes, it should probably be around.
Thank you. We're gonna keep $3,000 for just for working with you. It's not gonna be cheap, it's now a bit of fun, like. There it is. Thank you. That's so cool. Promise I'm constantly super teaching, so which would be great if I wasn't allowed during book session. And I also wanted to, you know, remember that. It's like, it's like post function. Yeah, I know. Not very nice, not very nice. What if you give me out?
Thank you. I just like yes. I'm sorry. I think it should be higher than the city. Higher. Because the further it gets away from that, the shallower it becomes, even from a term like this. So we're looking at, as you know, the point here, and then we get the point here, and so like this. I was gonna ask you, I'm sitting here. Yeah. Ask me about it. And it still doesn't exist. So -1/0. I enjoy that. Simplify the problem. Then. Yeah. Remove when you're at it. And remove when you're at it. What you're doing. It's like just, there's like 3 talk about. So true before. Like toward that next time I watch you on, but I'm stuck and like, yes, right. I feel like these are the oddly has it's like I feel just sitting down. Okay, so yeah, I didn't know about best right. You can look at honestly, I'm going to take over this thing my house. It is a test. Yeah. That's not going to do it. You're only time.
Oh my god. I need some math. We have sort of like the same thing. It's like, he's like, oh. Yes. I don't know. Is it? That's how I was trying. Yeah. Yeah. That was the. I think that's man. Screenshot. I see how I think the doors are like that. So instead, it's just my beach. So for that is. It's wrong, page 19. So basically, I'm going to just this. Screenshots. It's like, yeah, it's right. Because during the summer, I was looking for the I will use process. Makes no sense.
You could share.
I call it on and then they don't. I can't see that. I can tell you that on and then you plug one series. I already know it's far. Yeah, that's all.
So I think that's.
Yeah.
But you're only rolling the film.
So closer, I mean, it's. Remember.
Close to that.
Ready? Yeah. It's just continuing on conservation. So I can stand on the same weather. It's like that. Yeah. If you really have to get together. Yeah. There's so great. We have about but the porch is
Ladies and gentlemen, I show 2:00, which means the physical class is over. Tomorrow, 9 AM, 9:10, I will see you then. I was like someone at the beginning of class. If you have questions, I'm going over to the Richmond Center right now. I'll be there for the next hour and 20 minutes. And then I know we have tutors for this course. Send emails, start making appointments, talk to me. I will see you all tomorrow.
Like,